Chemistry powers today, but courageous chemistry is shaping our tomorrow. It's fueling the hydrogen economy and driving clean energy. It's in our semiconductors and even powers our 5G. It makes bridges stronger and medical equipment safer. Chemistry powers progress and binds us all together. But there's something more that sets us apart. Courageous chemistry.
Hello, welcome to today's lesson. In today's lesson, we'll look at volumetric analysis, which is a branch of practical chemistry, also called analytical chemistry, okay? In today's lesson, you will learn what volumetric analysis is. You will learn terms used in titration and what titration is. And then you should be able to form a table on measuring titration. So what is volumetric analysis? Volumetric analysis is a form of quantitative analysis involving the measuring of volumes of reacting solution. Okay, it involves the use of what we call titration. Now, analysis or analytical chemistry is divided into two main branches. We have the quantitative analysis and qualitative analysis. Quantitative analysis tells us how much of a substance is present, while qualitative analysis tells us what is present. Okay, an example of quantitative analysis, you will have what we call titration or gravimetric analysis. One other example of qualitative analysis will be determining semi-micro analysis and then determining organic spotting. What is titration? Titration is a measurement of volume of a solution of one reactant that is required to react completely with measured amount of another reactant. Okay, there are different classes of titration. Okay, we have acid-base titration, also known as a neutralization reaction, okay, which involves the reaction of an acid and a base, is it not? Yes. Then you have what we call redox titration. In redox titration, oxidation and reduction is actually taking place. You can see an example there, is it not? Yes, there is transfer of what? Electrons. So there will be an oxidizing agent and a reducing what? Agent. Then there's also what we have complexometric titration, all right? An example you can see there is zinc and EDTA. And then you have precipitation titration, titrating an halide ion with a silver nitrate. EDTA simply means ethylene diamine tetraacetic acid, all right? Terms you should know in titration. The first is called the titrant. Now the titrant is also called the standard solution, okay? It is a solution that the concentration is what? Known, and you usually put it in the what? Burette. Then you have the other one that is called the analyte. Another name for the analyte is called the titrant. Titrant. ND, okay? It is a solution with unknown concentration. In most acid and base titration, it is placed in the conical flask, okay? But it's not all in most cases, all right? Then you have another term known as equivalent point, okay? This is the point where moles of the acid equals the moles of the base, okay? Often marked by an indicator sharp change. We call it sharp change because at this point in time, the number of moles of acid equal to the number of moles of base. Unlike the end point, in the end point, we say it's the point where the indicator actually changes color, okay? Now, there's a difference between this equivalent point and the what end point. In an ideal situation, the equivalent will be the end point. That is, if you use an indicator that changes very sharply, but this is not mostly the case. So most times we have what we call titration error. That is a situation whereby the end point is a little further than the what? Equivalent point. That is end point minus equivalent point to give you titration what? Error. Take note of that. The goal of titration is also be able to determine the mole of the unknown and also, if possible, determine is what? Concentration. Take note. The next thing we'll look at is indicator. An indicator is a reagent, okay, that indicates the end point of a titration by bringing out a color change, okay, that is visible to your eyes, all right? The essential characteristic of a good indicator is that the color change must be clear and sharp, and then it must be indicated when the reaction is what? Complete. There are three main kinds of indicator that we use mostly in titration. You have methyl orange, you have methyl red, and you have phenolphthalein, okay? For methyl, you can pause this video and look at their pH, okay, and their color change. But know that when you have a strong acid and a strong base, you can use either methyl orange or phenolphthalein, okay? We have a weak acid and a weak base. You can use any indicator, but you have a weak acid and a strong base, you use phenolphthalein, okay? So strong acid, weak base, methyl orange. Weak acid, strong base, phenolphthalein. Let's look at some concentration terms. The first one we're looking at today is molarity. Molarity is defined as the number of moles of solute present in 1 dm cube, okay? The unit is mole per dm cube. Then you have normality, which is the number of gram, okay? The gram in 1 liter or dm cube of a solution is also expressed in gram per dm cube. Then you have what we call the strength of a solution, okay? It's also expressed in as molarity times molar mass, or normality times equivalent weight. All right, so these are the concentration you will come across at this level, okay? Again, we'll look at standard solution. We say standard solution is a solution whose concentration is what? Known, is it not? Yes. We have two types of standard solution. We have the primary standard and the secondary standard solution, okay? Primary standard, their concentration does not change easily. They can be stored for a long time, okay? While secondary standard, their concentration changes easily. An example of secondary standard is sodium thiosulfate, all right? How do you prepare standard solution, okay? Normally, you might be asked to state the step involved in preparing standard solution, or you can be asked to calculate the mass required to prepare standard solution. But know that we prepare standard solution not in a conical flask but in a volumetric flask. So let's take the calculation part. For example, they say calculate the mass of sodium hydroxide needed to make 250 cm cube of a 0.125 mole per dm cube standard solution. Now 0.125 mole per dm cube, that unit tells you that it is concentration, and that concentration is called the molarity, okay? Mole per dm cube, remember? Yes. So what you do here is to rearrange your equation, okay? So moles become mole per dm cube times volume. You now convert your 25 cm cube to dm cube by dividing by 1000, okay? So now that you've gotten the mole to be 0.03125, remember, number of mole equal to mass over molar mass, is it not? Yes. We now convert mass, is it not, to be mole times molar mass, is it not? That gives us 1.25 gram, all right? Now that I now know that this is the mass I need, what do I do next? Step 1, I will 0 to 2 decimal place of that is my weighing balance, and then I will measure 1.25 gram of sodium hydroxide into a small beaker. Step 2, I will dissolve the sodium hydroxide in a small amount of distilled water or deionized water. Step 3, using a funnel, I will carefully transfer the solution to a 250 ml volumetric flask. Step 3, I will rinse out the beaker with distilled water and add washings to the volumetric flask. Then the next step, make the solution up to the graduation where the 250 mark is with distilled water. And then the final step, stopper the volumetric flask and invert several times to mix thoroughly. There you go. Common apparatus in titration: you have your conical flask, you have your pipettor, you have your glass dropper, and then you have your conical funnel. You should note the following precautions while taking the reading. In fact, this video will help you. Pay attention, alright?
When chemists analyze solutions to learn how much of a certain substance is present in a sample, they may use methods of volumetric analysis. These techniques involve the careful measurement of sample and reagent volumes. The most common types of glassware used for volumetric analysis are the burette, the pipette, and the volumetric flask. The burette is a long calibrated tube fitted with a stopcock valve and nozzle. To use the burette, first rinse it with deionized water by filling and emptying several times. The rinse water must be flushed out so that its residue does not dilute the reagent to be used in the tube. To do this, use a funnel to add 5 milliliters of the reagent to the burette. In removing the funnel, be sure to clear the neck of the burette before twisting the funnel downward. If you don't, the stem of the funnel may break the glass at the top of the tube. To rinse the burette with the titrant, Hold the tube in the near horizontal position and rotate it to rinse as much of the inner sides as possible. Then discard the rinse. Repeat this step twice more, then fill the burette with the same reagent. Fully open the stopcock to flush out any air bubble in the nozzle. If the bubble escapes during the titration, error is introduced. Stubborn bubbles lodged near the stopcock can be removed by giving the burette 1 or 2 vigorous shakes while it is draining. As the camera pans upward, observe how the back half of each line gradually becomes hidden by its front half as the camera's view becomes horizontal. To avoid parallax error, your view line also must be absolutely horizontal. Adjust the initial reagent level to anywhere between 0 to 2 milliliters. Hold your finger or a white piece of paper behind the burette to facilitate the reading and read from the bottom curve of the meniscus, estimating the hundredths place. Now you are ready to begin the titration. Initially, you may add the titrant rapidly while swirling the Erlenmeyer flask. The indicator will begin to change color in regions of high titrant concentration, but with swirling, the color will disappear before the equivalence point is reached. Slow down the titration when the color change becomes more pervasive and begins to linger throughout the flask. Add the titrant dropwise at the end. At the very end of the titration, you can add a split drop by touching a hanging drop of titrant on the nozzle to a stirring rod, then stirring it into the solution. You are looking for the one drop or split drop that causes the color to change for at least 10 to 15 seconds. If you are careless, however, perhaps working too quickly, you may overshoot the endpoint. In the case of this acid-base titration with the indicator phenolphthalein, the bright pink color shows that this has happened and that this trial must be done over. For good trials, be certain to record your final burette reading directly into your lab manual.
Burette readings must be recorded in a table as shown, with appropriate headings and units. All burette readings taken from the burette must be recorded and given to 2 decimal places with the last digit given as either a 5 or 0. Readings must be recorded in ink immediately after they are taken. The volume of the titrant added is the difference between the final burette reading and initial burette reading and must be recorded in the same table. A tick is written to indicate consistent reading. To calculate the volume of the titrant added in the experiment, take the average of the 2 consistent readings and then round off to 2 decimal places. In the example above, the average titrant volume is calculated by taking the average of the 2 consistent readings, 25.65 and 25.60 cm3, which are within 0.10 cm3 of each other. The value is then rounded off to 2 decimal places to give 25.63 cm3.
That now brings us into the lesson. Do your other activities. Stay safe.